So we're very happy this week to have Anja van der Linden. She is a professor at Stony Brook University in Long Island. And so Anja got her PhD at MPIA in 2007, I think, and Munich University, I guess, technically.
Yes. And MPA, technically.
And MPA. With Simon White. And then you had a postdoc in Stanford at KaiPac. From there until 2015, where you got the faculty job.
Yes.
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 So Anja has done some extremely interesting work in the field of weak lensing, and she's a member of LSST and Euclid. And I think you're going to be telling us some of the work that you've been doing on, like, with weighing the giants, right?
Yes.
And so you're going to be telling us about cosmology with galaxy clusters. So there you go.
All right, very good. Well, thank you very much for inviting me. This is an exciting place to go. Also on Long Island, we had no snow this winter, so I feel like by coming here, I get to make up for that. All right, so I'm gonna tell you really broadly about what the current status of doing cosmology with clusters of galaxies is. And actually, as Laurent said, I've been working on this for a while. But I think it's also a pretty exciting field where there's a lot of techniques. We have a lot of things to work out, but there's also a lot of potential. Now, I realize that not everybody in the room might be a cosmologist. So I'll go through a brief introduction of kind of the basic things that we need as a background to my work. In a big picture world, cosmology is actually really successful. Our observations for cosmology really split into two sets. On one hand, we have observations of the cosmic microwave background, so our baby picture of the universe, right? Just some 400,000 years after the Big Bang and after the inflationary period. The other sets of observations really are local. This is after the structure in the universe developed from the very smooth CMB, and structure developed into the galaxies, the clusters of galaxies, stars, planets, everything that we see today. And despite these observations being very different and like spanning almost the entire time frame of our universe, we can describe our observations by actually a very simple model with just 6 parameters. Okay, and that's actually really good fit for most of our observations. The challenge in cosmology is that this model really requires at least 2 components that we don't really know much about. So that is dark energy. By dark energy, we mean that as the universe starts to expand, we all expect that expansion to slow down because of gravity, right? Because of dark matter, normal matter attracting each other, we expect expansion to slow down. However, lately we see actually that the expansion is starting to accelerate. It's expanding faster. And we just call this dark energy because we have no idea what it is. Our cosmological world model also requires that we have dark matter. So some form matter that attracts gravitationally, but we don't know what its particle nature is. And that's a bit of an issue on a grand scale. Well, only roughly 5% of the energy density in the universe is in a form of matter that we can describe, let's say, with the standard model of particle physics. Stars, planets, gas belts. Cosmologists will just call them baryons, and we say we pretend that we understand them. I know that this is not true, but on a cosmological scale, you know, these 5% is a pretty small fraction. And then roughly 75% or 70% of the energy density in the universe is in this form of dark energy. And there's a few things that it could be. The simplest explanation, which actually is a good fit to the observations, is that dark energy is simply a number, a cosmological constant which Einstein introduced into the field equations. So that means we just have a single parameter lambda with an equation of state. So that's the ratio of the pressure to density that is fixed to -1 and does not vary as function of time. This is still a great fit to all of our observations. However, there is no satisfying theoretical explanation. And so a lot of cosmology now is to identify whether W could actually vary as a function of time and be slightly different from -1. So a lot of the funding that goes into cosmology experiments is actually to try to measure W, this equation of state. There are other things that dark energy could be, such as modified gravity, but in terms of measurement, this is one of the prime things that we're trying to measure. Then there's also roughly 25% of dark matter. Dark matter is really important as it drives the structure formation in the universe. And I'd say clusters are actually great dark matter laboratories but I'm not going to talk about that aspect as much today. On the particle side of things, there is an interesting aspect in that cosmology can also actually put an upper bound on what is the species summed mass of neutrinos. And that is interesting because our standard model of particle physics has a really hard time explaining why neutrino masses are so small. And so this is actually where cosmology can inform particle physics and particle physics experiments. All right, so there's going to be some plots with result and contours. So I just want to briefly go through some of the symbols that those will refer to. Cosmological probes in the local universe at a base level in the 6-parameter model, really what they constrain is 2 parameters, mostly. One is the total matter density, so that's the amount of dark matter, but also baryonic matter, the sum of those. And the other one is sigma 8, which is the amount of structure that is in the universe. And so, yes, this is the amplitude of the power spectrum measured on a scale of 8 megaparsecs. This doesn't tell you anything. Imagine you take the universe today and you take giant ice cream scoops that are 8 megaparsecs big, and you just scoop out a lot of, bowls of ice cream. And you just measure the standard deviation of how much mass in each of those scoops of ice cream is. So really what that matters, that's what that measures. In the simplest case, we're trying to fit the 6-parameter model. What we do is that we fix the 4 other parameters to the CMB, and then we measure omega matter and sigma 8. So that includes that we fix the geometry to be flat. So that means that there's no curvature in the universe, and omega matter and the dark energy density add up to 1. It also means that we fix the equation of state of dark energy to -1. But we can also fit for more parameters. So that includes that we actually go from a 6-parameter to, say, a 7-parameter model, and we start to fit for the equation for W for the equation of state. Or we start fitting for neutrino masses or other things. All right, so how do we use clusters of galaxies in cosmology? This is a cartoon version of what we're going to try to do. This is a simulation, just an n-body simulation, where I ask some of the n-body simulators to color dark matter halos with a circle each time the mass of that halo crosses a certain threshold. So we see structure assembling in the universe. We go from a pretty smooth matter distribution to matter forming clumps. And then once we have these halos where the mass inside becomes very realized, we can say, all right, we have a halo of dark matter of some certain mass. And over here, we're keeping track of how many halos with a given mass we have. This is called the halo mass function. And as you could see, it evolves as a function of time. The evolution of the halo mass function and actually its shape, they're very sensitive to our cosmological model. What I mean by that is, imagine simulators had put in more dark matter in here. That would mean that structure assembles faster. That means the halo mass function would evolve quicker. Vice versa, if we add more dark energy drives things apart, it makes it harder for structure to form halos, and so this would evolve more slowly. Likewise, if we change the laws of gravity, if we add warm dark matter, all of these things can change the shape and or the evolution of the halo mass function. And so this is a function both of the growth of structure, well, obviously, but the nice thing for cosmology is also that this is a probe of the geometry of the universe, because we're measuring number of halos in a volume, right? And actually 3-dimensional volume, whereas things like supernovae, they probe 1 dimension of the geometry, right? They probe distance. All right, well, great. So these massive halos, those are things that we can find on the sky. They are clusters of galaxies. The clusters of galaxies are the largest gravitationally bound objects in the universe. They have the properties similar to this cupcake. They are very much dominated by dark matter. So that's the chocolate part, 86% or so. Then they have roughly 10% of hot gas. If Julie were here, she can tell you all about the hot gas in clusters. And then we have some sprinkles of, well, mainly red galaxies on there. Okay. And so, clusters are maybe one of the oldest cosmological probes. They were one of the first places where we found evidence for dark matter. And we're good at identifying them, either by the hot gas or actually by a bunch of red galaxies. Currently, for doing cosmology with the halo mass function, we have samples of a few hundreds to a few thousand clusters right now. However, in the very near future, with upcoming surveys such as LSST, Euclid, but also Eurosita and the X-rays and SZ surveys, we're going to have many more, tens of thousands, if not hundreds of thousands. And so there's huge statistical potential. And a few years ago, Cosmic Visions report came out, and it actually, like it quotes, it writes, the number of massive galaxy clusters could emerge as the most powerful cosmological probe, but it has an if statement. And that if statement says if the masses of the clusters can be accurately measured. And basically, this if statement is the rest of my talk. Right? So the next slide, I'm going to show you where we're at with these samples. So this is a figure from a paper by, from the DS cluster cosmology analysis. And to guide your eye, the blue contours are the Planck measurement from the primary CMB. All right, so this is kind of everybody's standard measurement of our standard 6-parameter universe. The red contours are a different probe of local cosmology. It's from dark energy survey. It's combining 3 2-point function measurements. These all also constrain the growth of structure or the amount of structure in the local universe. So those are the red contours. And you know, there's a whole thing about whether these red contours are offset on the blue contours, but it's only 2 sigma, so maybe yes, maybe no. In gold are the cosmological constraints among the giants, which I'm going to talk about. These are clusters that were selected in the X-rays. In purple is something quite similar. These are clusters that are selected by the Sunyaev-Zeldovich effect. I'll get back to that later. So these contours are actually quite, they're in very good agreement with both Planck and the DS3 plus 2-point results. So by now, you've probably spotted those gray contours. The gray contours are from clusters that we select in the optical by the galaxies. These are the largest cluster samples we have. This is the one with a few thousand clusters. But this result is actually the 5 sigma tension from Planck, driven by its low value of omega matter. And we're still trying to figure out why that is. And so this is the other part of my talk, really. All right. I should also say if somebody has questions or want me to repeat something, then please feel free to interject.
What's the difference between like cosmic shear and galaxy lensing?
Galaxy lensing is position cross shear. Cosmic shear is shear cross shear. And then galaxy clustering is position cross position. All right, so in the rest of this talk, I'll go over kind of how to do cosmology with the halo mass function. I'll discuss some of the current results awaiting the giants, and of course, quite a bit of what might be going on with the dark energy survey results. And if I have time, I would like to talk a little bit about Rubin Observatory and LSST. All right, so in practice, how do we actually go and measure the halo mass function and its evolution? So the first ingredient, we need simulations like the one that I showed. And we need simulations run with different sets of cosmological parameters and their predictions for the halo mass function, so the number of halos as a function of mass at different redshift. We then go out and we find clusters, say by the X-ray flux or by the number of galaxies or by their shadow on the microwave background. And then we need a relation between the mass of the halo that's in the simulations and whatever it is that we actually find clusters by, because these are not the same thing. And you can already tell that this is kind of non-trivial. This is also non-trivial because all of these things ultimately depend on cosmology. The halo mass function by construction. Our measurements actually also depend on cosmology. So here I'm showing an example from X-ray survey, where on the y-axis we have X-ray luminosity. We don't measure X-ray luminosity. We measure a redshift for the cluster, and we measure a flux. But to get the luminosity from a flux, we actually have to assume a cosmological model, right? So our measurements here on the y-axis, on the x-axis also depend on cosmology. So all of these things are interrelated. So we also need a statistical framework to solve for these things. Finding clusters, in a way, is an easy thing because we see lots of clusters, but it's also in a way complicated. But anyway, in the simulations, we have these massive halos. And then on the sky, we can find clusters either by the 12% hot gas, so either by the X-ray emission that comes from the thermal bremsstrahlung, or by the Selldovich effect, which is just inverse Compton scattering of CMB photons off of that hot gas. Or we find them in the optical as overdensities of galaxies. And this works best if we're actually looking for red galaxies, at least for clusters in the local universe. So let's say less than a redshift of 1 or 1.5. Okay, great. We find lots of clusters. But the problem is that our observable, so X-ray luminosity, SE shadow, number of galaxies, that's not the cluster mass. All of these correlate with mass in the sense that if you have a cluster that is much more X-ray luminous than the other one, then probably the one with a higher luminosity is more massive. But it doesn't have to be. This relation has considerable scatter of the order of 20 to 40%. Do we actually need to know the mass of every cluster in the survey? No. It's enough if we know how to describe the population. So the probability of the value of our observable given the halo mass. All right, good. Clusters are very complicated. They're also maybe relatively simple, at least as a population. And so in the simple assumption, we can actually assume, and this is pretty good assumptions, that the mean of our observable follows a power law relation with mass. So if we plot log of our observable versus the log of the mass, we can expect the mean to be roughly a straight line. On top of that, however, we have intrinsic scatter. So at a given mass, the observable can scatter up and down. And so if we just sample this, so we sample from the mean relation, we sample up and down, and then we impose our flux limit, saying that we can only see clusters with, let's say, more than 20 galaxies, or above a certain X-ray flux. Then we go from a population that's the blue and the orange points combined to only the blue population, right? These are the clusters that we see, only the blue ones. Now, of course, in the observations, we don't actually have the x-axis, right? We only have the y-axis. So if you want to go and bin this up, all we have in the observations is some number of clusters in bins of the observable, right? And to do cosmology, what we need is actually this relation. In each of these mass bins, what you'll see is that, well, there's a few clusters that have scattered down. There's a few that are on the mean, but really most of the clusters we see have scattered up. And that's because globally, there's just a lot more low mass clusters than high mass clusters, all right? So going from here back to there, that really is why cluster cosmology is hard. So that's the if statement. All right, so to measure masses of clusters, we need observables that actually probe the gravitational potential, right? Because the number of galaxies doesn't really tell us anything about the mass of the cluster by first principles. We have a few tools for that. X-ray hydrostatic masses have played a big role in cluster cosmology. This is where we assume that the gas in the cluster is in hydrostatic equilibrium, which lets us solve for the total mass. However, the gas is not in hydrostatic equilibrium, and so this comes with certain systematic uncertainties. We can try to use the dynamics of the galaxies in the cluster to measure the velocity dispersion, use the Vera theorem to infer the mass. This has very large scatter and is biased too. Or we can use gravitational lensing, in particular weak lensing. And so this has shown that, yes, it has a lot of scatter, but on average, actually, it's an accurate mass measurement. All right, so specifically, I work on weak lensing of clusters in the optical. I know you're strong lensing people here. And so you probably used to see very pretty examples of gravitational lensing. And you could tool version what it is that I do. So let's imagine all the galaxies in the universe are actually circled, right? These are the background galaxies. And now we put a cluster in front of them. That cluster is kind of right in front of the red galaxy. That red galaxy is then lensed into these multiple images and arcs. So this is the regime of strong lensing. Strong lensing is great, but for clusters, it only probes the very center. Okay, it doesn't really probe the total mass of the cluster. But you can see that as you go further away from the center, the galaxies further away, they are tangentially sheared. They're tangentially distorted, and they align right? So tangentially towards the direction to the cluster. So if all the galaxies were round, great. You have one measurement of this distortion, which here, and that is an estimate that you can use an estimate of the mass. Of course, galaxies are not actually round. Okay, so we can assign vorticities to galaxies, and then we lens them. And then what we need to do is actually average over all of these galaxies in order to estimate the shear and thus the mass. All right, and so if you get these pretty HST images of clusters, so the baby bullet cluster, strong lensings here and here. And the larger image, this is some of the ground-based data that I work with. And the Hubble image is really only the core. It's only this white square probing the very core of the cluster. I'm actually interested in what is the mass out here. Okay, so we measure much further away than what the Hubble picture typically shows. All right, so in practice, we need to measure the shapes of these galaxies, right? We want to measure the ellipticities as a way to estimate the gravitational lensing shear. We also need to measure the redshift of the galaxies, and we actually need some assumption on mass distribution. But with these ingredients, we can infer the mass of a given galaxy cluster. Sure.
So instead of like doing this for like a set of galaxies so that you kind of calibrate your like scaling relationship there, couldn't we just do this for everything?
Instead of a set of galaxies or a
Because
set
now,
of galaxy
based on what you
clusters?
said earlier is that you're gonna basically seems like you want to be measuring these like influencing masses so that you calibrate this like, you know, kind of like, you know, your n observable relationship, right? Or couldn't we just like do this for every cluster?
So I do it for every cluster actually.
Okay.
But I'll actually get to this. Right? Okay, but let's just in principle, let's say we can do weak lensing cluster masses, right? But weak lensing cluster masses are very noisy because like this is super high signal to noise ratio measurement for a weak lensing signal, right? In general, they look way worse. All right, so on average, meaning if I bin clusters with a certain mass range, I get the correct average mass of those, but each measurement can be far off, right? So for ground-based observations of massive clusters, the total scatter is of the order of 30%, right? 20 of that is actually intrinsic, like the weak lensing measurement for single cluster is not going to get better than that. So what that means is if I go back to, well, all I have is bins and observable. So I take a given bin, I measure some kind of weak lensing measurement of all of these, but really what I'm measuring is the average. So what I get then is you can do this by eye, right? The average is somewhere here, there, and there. So I get these red points. Red points are not the black line. Okay, if I only have the red points because I only measure the average mass, I need to assume a slope and an intrinsic scatter if I want to reconstruct that line.
I guess my question was that so you're saying this scatter is in the scatter of the observable for a given mass, right?
Yes.
The intrinsic scatter of that. But if you have the weak lensing masses all together, why can't you just do cosmology directly on that? Like, why do I even need these observables?
Let me explain the rest of this. All right. So these observables, we need to actually find the clusters. Right. So this is where that comes. This is just the number of clusters that I've counted in relation to mass. Everything else is trying to calibrate this relation. Right, but this is for the actual way by which I counted clusters. There's a whole different argument. So there are groups that have tried to do cosmology with weak lensing selected clusters, and it works terrible. And we can discuss that maybe after colloquium, but if I go into this now, I'm not finished.
Because of selection.
Because the weak lensing peaks do not have a one-to-one correspondence with gravitationally bound halos, because you have things like filaments or groups. Things along the line of sight will easily look like a weak lensing peak, which is not actually a cluster. This is where peak count statistics comes in. So the right way to do it is actually to do peaks, weak lensing peak count statistic and not halo mass function. All right, but let's get back to this part. Okay, so weak lensing alone is not enough to measure this relation. All right, so in what my group does for cluster cosmology, we do not only just do weak lensing masses, we also use additional observations of these clusters in X-rays. Pity Julie isn't here. Anyway, if we have our clusters and we follow up a subset of them with Chandra or XMM, we can measure some properties such as the temperature, the mass in the hot intercluster medium, or the product of these two. And all of these properties have a much lower scatter with a true mass than the observable themselves, okay? They're still not the mass, okay? But imagine if I have these red points, and even if I don't know their relation with true mass, if I have these red points, I can reconstruct the slope and the scatter of this relation, okay? But for figuring out the total normalization, this is just where we are to weak lensing, okay? So we have the combination of these low scatter mass proxies, which give us the shape, that is the slope, and the scatter of the mass observable relation. And we use weak lensing to anchor that. All right, and so this is what we set out with Ring the Giants. We started with clusters selected from the Rosat All-Sky survey, which flew in the 90s. So it took a while to get cosmology out of that. Our cosmology is based on roughly 200 clusters from the Rosat survey. We have weak lensing observations for roughly 50 clusters, and we have Chandra X-ray imaging for these low scatter mass proxies for about 90. But a lot of this work really goes into building a self-consistent framework for how to integrate all of these observations and cosmology into the same analysis. So there's a bunch of people, and I'll say our total area is 10 square degrees, which back in the early 2000s was a lot, but nowadays there's a much larger surveys. There's a bunch of paper from a while ago now that go into how to do the weak lensing part and how to do the cosmology. Our analysis is a hierarchical analysis. It's very much a forward model where every cluster actually enters the analysis by itself. Okay, so we're going to try to model every cluster with its survey observable, such as the X-ray luminosity, its weak lensing mass if it has one, and its X-ray low scatter mass proxy if it has one. And so in this case then, because that's the population that we're trying to model, the parameter of the scaling relation, so things like the slope and the intrinsic scatter and the mass normalization, and cosmology, they're actually hyperparameters in this analysis. All right, so they drive the priors that we put in each cluster. And all right, here's a very sloppy notation way of how that works. We have the parameters of the mass observable relation and our cosmology parameters. Cosmology will predict the cluster mass function, so it gives us probability of a given mass, given cosmology. Mass observable relation, that gives a probability for a certain observable, given slope, scatter, etc. True mass, and cosmology, because we usually have things like angular diameter distances. And then we're good Bayesians, and we can put some priors and invert that and sample that. And there's my cartoon version of the same thing. We put in halo mass function predictions, our cluster observables, our X-ray observations, weak lensing, and outcomes cosmology and scaling relations. And I think this is the only image that I have of reconstructed scaling relation. So this is X-ray luminosity as function of mass. And the green line is our best fit mean relation. And notice how most of the clusters that we've detected actually scatter up, right? So that's the same way as I showed in the cartoon. All right, I very briefly go over our cosmology results. Sigma 8 omega matter for clusters, it's actually pretty independent whether we fit 6 or 7 parameters. It's well consistent with the CMB. So in modern terms, we don't see any evidence for S8 tension. We also don't see any, we don't actually have a measurement of a non-minimal neutrino mass either. In terms of W, so our results are the purple ones. And it's actually quite nice because both for W versus sigma 8 omega matter, we're pretty nicely constrained. It's not a huge degeneracy phenomenon. And so we actually still compare well to other single probe measurements of W. If you combine a bunch of measurements, you get something much tighter. But in terms of measurement from a single probe, at 15%, we're still one of the tightest. And I'm going to skip the Planck part. can ask me questions about that later. All right, so that's I would say that's the state of the art in X-ray scope. State of the art in SC selected clusters is the analysis from the South Pole Telescope. This is actually very similar to Ring the Giants. So it uses the clusters with a hierarchical analysis, with weak lensing follow-up, as well as with X-ray follow-up. And the results are actually in pretty good agreement with Ring the Giants. In terms of hierarchical analyses, of clusters, there's currently 3. So there's Ring the Giants with these 200 clusters, SPT with about 400. Now I'll say that Zabelde and Challenor did a reanalysis of Planck with about 400 clusters. They didn't use optical lensing, but they used CMB lensing masses, and they're also nicely consistent with the other 2, as well as with Planck CMB. All right. Questions so far? Before I switch gears and talk about DS? All right, so in terms of X-ray selected and SC selected clusters, things look good, okay? Not much to be concerned about. So I'll now talk about the results from selecting clusters in the optical, specifically results from the dark energy survey. So the dark energy survey is an optical survey conducted with the CTAO Formula telescope, covers 5,000 square degrees in the south. And they've been doing lots of cosmology. Again, one of their arguably most competitive results are from doing these 2-point statistics, just a gray contours compared to Planck, never comparable measurement of W. All right, DS was actually in a way motivated to do cluster cosmology. And so in a way, there's actually a lot of pressure to get this analysis out. And it took a while because it's pretty complicated. So in DS data, we identify clusters by the red galaxies. It's called a red mapper algorithm. And with the DS data, the algorithm finds some 6,000 clusters, right? There's an order of magnitude larger than the other samples. Because this is so many, and each cluster has very little information with it, the analysis here is not done hierarchically, but it's a binned analysis, right? Computationally, at least a few years ago, we're not in a position where we can do this for 6,000 clusters. And so the binned analysis goes and bins galaxies by, in bins of redshift, and in richness, that's the number of galaxies. And then the weak lensing comes in is that we take bins of these galaxies, we stack their shear signals, and then we measure an average mass for the clusters in this bin. One thing to notice that when you giants in SPT, we only fit for the main part of the halo. We call it one halo term. DS goes and fits out to very large radii. All right, so up to almost 100 megaparsecs. And so they fit beyond what is the very light region, and we call that the 2 halo term. The product from the weak lensing analysis is then average mass in a bin of richness. All right, this is flipped from my notation. I usually put mass on the x-axis and the observable on the y-axis. But because they're measuring in bins, this is mass as function of observable, right? And so the product is a red line and a reference cosmology. All right, so how did the results from the 6,000 clusters end up over here? What does it tell us? It's unlikely that everybody else is this wrong. Okay, this was a discussion after the unbinding. Is this the only true result? Probably not. It's also unlikely that the input for the weak lensing analyses, that is the shear measurements and the photosees, are so wrong to produce this result, because if they were wrong, then also the 3 + 2 point results would be wrong, okay? Or at least very offset complaint. What is more likely is that our model of the relation between the observables and the halo mass is actually incomplete. And I'll say that it actually took, I think, at least 2 years, because between unblinding the analysis and actually putting out the paper, because this was so far off that they just went back and reanalyzed a lot of things, particular of this aspect. However, the constraints actually, they didn't move towards the blue, they actually moved further away. So we don't know what that is. So, you know, as a cluster person, you might be tempted to say, okay, this is a problem for optical cluster cosmology. However, really, the optical people are the first ones that are probing down to the low masses that we want to access for cluster cosmology with X-rays and SC as well. So I think if we have a problem in the optical, we should anticipate that everybody in cluster cosmology is going to have this problem. All right, so where does the tension come from? In the analysis, there's really three moving parts. One is the measurement of the number of clusters, so how many clusters did we count? One is the relation between the halo mass and the richness, or number of galaxies. And the third part is cosmology. So in a cluster cosmology analysis, well, we have a measurement of the counts and our measurement of the scaling relation from the weak lensing stacks. We leave cosmology free, and that's the result. We get this tension. So when we saw this, everybody immediately said, well, it must be the weak lensing, because, well, it's much harder to do weak lensing than to count clusters. So what happens if we leave the mass richness relation free, and we fix the number count and we fix the cosmology? And so now we're solving for the relation between mass and observable. And the result of that is the black line. The result of the weak lensing analysis is the blue line. And so these two actually differ, especially at the low richness clusters. Okay, we get a different slope. And at low masses, the normalization is quite off. And so in a way, that's saying that the tension is driven by the low richness clusters, which is what you would expect. Because for massive clusters, we actually think we understand. All right, I think I'll skip this. Right, so if there's something wrong with the mass richness relation, then I think in hindsight, we actually had some warning that this is the case. This is work by my postdoc, Taeyun Chen, as well as some other people. Taeyun is an expert in measuring the splashback radius. And so he measured the splashback radius in SE selected samples and in the optically selected samples. But he found that the measured splashback radius, this is a radius that's kind of the edge of a cluster. That measurement, if we assume the DS weak lensing masses, is actually smaller than predicted by simulations. So that actually shows us that there's something off between the simulations and our mass richness relation. Other people have shown that this really points to issues in how we select clusters based on red galaxies. All right, so what could be going on? To me, this is a way of asking, okay, what is it that scatters up? Right, in my cartoon, I have a power law relation with log normal scatter, but is there something else? What is it that makes clusters scatter up? The first thing that we can ask is, well, are these low richness systems real? In the sense that if I find 20 red galaxies, is there at least one massive halo along the line of sight? Or maybe is it just 20, relatively small halos along the line of sight, which, would be somewhere over here. The people from the South Pole Telescope SC survey, which overlaps the DES area in a large degree, they went and basically asked for every red mapper cluster whether they see an SC selected cluster. And they found that they confirmed fewer red mapper clusters than what would be expected given the SC scatter and given the optical scatter. So in this somewhat confusing figure, the histogram, that's the number of clusters. So note that this basically cuts off at a richness of 40. So everything below that is an extrapolation. But if the DS weak lensing mass observable relation were true, we would expect a number of, say, 10 to 20% of clusters that are not confirmed. Instead, they find even at 40 that roughly 60% are not confirmed. Extrapolating that to a low richness cut, they get a very large fraction of contaminants. In a way, that would mean is that there's a bunch of, it's galaxies, there must be a halo somewhere, but it could be a bunch of galaxies with much lower masses, which have found a way to scatter up. I've been working on this using X-ray follow-up. So taking a subsample of clusters at relatively low richnesses and pointing swift at them until we see some X-ray luminosity. Now, almost all clusters have some X-ray luminosity, saying that yes, there's a massive halo there. However, in this figure, this is the measured X-ray luminosity, the luminosity that we would expect if all of the 30 galaxies were just field galaxies. So field elliptical galaxy is still going to have an X-ray emitting halo, right? And so if I have 20 of those along the line of sight, I expect some X-ray luminosity. If I have an actual cluster, that X-ray luminosity should be much higher. For most of them, the X-ray luminosity is higher, but in the tail, those actually could be just projections of 20 or 30 isolated field galaxies along the line of sight. Okay, so if this is a relation of average mass given richness, and I add a bunch of halos that have very low masses, that would actually naturally drive down this relation at low richnesses, right? So maybe the measurement is actually correct. Maybe in the sense of that with average mass given richness, weak lensing maps stacks are correct. So with our three pieces, what we can still do is that we fix cosmology and we fix the mass observable relation, but we leave the number counts of clusters free. So if we do that, we actually find that we predict more clusters than we observed. Okay, so to reconcile that with the observations would require that RedMapper is actually 25 to even 50% incomplete, and this is very unlikely. All right, because we think that every dark matter, every massive dark matter halo is at least going to have one galaxy in there, right? And at low redshifts, we actually also know that these are galaxies. So, you know, maybe 10% fine, but it's not 50% incomplete. Okay, at this point, I actually like to go back and think about, well, what can cause the scatter, right? What causes these clusters to scatter up or down compared to the mean relation? Well, there's many sources of scatter, some observational, but a lot of it is physics too. And in particular, there's triaxiality and projection effects that we need to deal with. So in the simulations, this is what a halo looks like, right? It is highly structured. It has a lot of substructure. It has filaments feeding into it. In our model, it's a spherical thing, right? And maybe this is just too simplistic. So if we move away from our spherical cow approximation, the first step would be to say, well, halos are really triaxial or ellipsoids, right? Football, American football shaped things. So let's imagine we have an ellipsoid, and an ellipsoid that is aligned along line of sight or is aligned in the plane of the sky. If the major axis is aligned along the line of sight, what happens is that in terms of projected mass, I now have a higher surface mass density. So I take, my galaxies, I turn the cluster this way, I suddenly see a higher density of galaxies in that part of the sky. And I also see a larger lensing projected mass, right? So in this configuration, I'm going to overestimate the lensing mass, and I'm going to overestimate the galaxy richness.
The integrated mass.
No, but I'll come to why. Well, so my reference is because cluster cosmology works with spherical overdensity masses, right? So it actually is relative to something that would be round, and it's out to that radius. The other answer to that is that there's actually projections that the filaments that feed into the cluster are highly aligned with what the major axis of the cluster is. All right, so these two things are sort of different, but they correlate very strongly. So either way, you end up with an overestimate. Vice versa, if the halo is in the plane of the sky, I underestimate the lensing mass and the galaxy richness. For lensing, so specifically, so even the triaxiality itself causes the scatter because we usually just fit parametric models such as NFW, and that will naturally lead to you doing the overall underestimate. All right. This also means that the scatter in lensing and richness is expected to be correlated to a lesser degree in SE. So what I mean by that is I have a mean relation between mass and lensing mass, and another mean relation between lensing and richness. And if a cluster scatters up in one of them, it's likely to scatter up in the other one too. Yes.
Concentration and rebirth.
We fixed the concentration and calibrated that on the simulations. but we also fit really far out.
Supposedly, if it was a three parameter, and marginalized over.
So for the individual weak lensing masses, the signal to noise is so low that if you're trying to fit two parameters, you just get a huge degeneracy curve. So you end up becoming very sensitive to what you assumed the concentration is, which is where you need it to calibrate on simulations. I have a student who's implemented a hierarchical way of getting a concentration distribution too, but it's not part of the cosmology yet. All right, so, okay, clusters are triaxial. As I just mentioned to Yashar, that also correlates with the filaments, right? So we expect the main filaments to be extensions of the major axis. And people have started to look in spectroscopy of what the redshifts of the red mapper cluster members are. So the cluster finder goes and finds red galaxies in optical imaging. And then basically we go and take spectra. And if a galaxy is actually part of the cluster, it's going to be basically at the same redshift. However, what we find is that roughly 20 to 30% of the galaxies are actually at larger redshift differences relative to these clusters. So these galaxies, these 20 to 30%, they're actually residing in filaments outside of the clusters. Now, this is again a stacked measurement. It doesn't actually tell us whether every cluster has, 25% galaxies that are projected, or whether 25% of the clusters are just projecting this. The answer is going to be somewhere in between, okay? It does look like it's relatively rare that there's no cluster and it's just a filament. Okay, so we have triaxiality, which will cause scatter up and down. We have projection effects. We expect these to be correlated. So when the richness is biased high, the lensing is biased high. There's nice work by Heidi Wu and others who kind of went back and redid the whole DS cluster cosmology calibration of simulations. And she measured in all of these spins, she measured the correlation between the scatter and richness and in lensing, and finds that it's the correlation is always positive on all scales, like we would expect based on what I just said. All right. So now that we have some physical understanding, is this enough to explain the DS cosmology results? So to explain the results, what will need to happen is that we take a true input mass-observable relation, that would be the black line, and we shift it down at the low masses, right? So that would, shifting out the blue line would actually fix our cosmology. So that would mean that the average lensing mass needs to be lower than the average true mass. And you can actually work in the power law plus log normal scatter. You can actually work out the relation between the mean mass given my observable and the relation of the stacked lensing mass given my observable. And so there's an additive term here where beta is positive. These two sigmas, they're scatters, and this is the correlation coefficient. Now, to explain the cosmology, this number needs to be smaller than that number, but there's no way to do that if the correlation coefficient is also positive. Right? If we only have positive correlation, which is our physical intuition, the weak lensing mass needs to be larger than the average true mass. Okay, so this goes the opposite direction. Okay, and this is why just accounting for projection triaxiality was not enough to fix the DS cosmology results. So we still don't know. Clearly, however, going away from the spherical cow to trying to account for projection effects is a really important part of the puzzle. In my group, we've been trying to look for hints in the data that can serve as proxies for the halo orientation. So is a cluster line along line of sight or in the plane of the sky? And so we've done this with central cluster galaxies. So if we have our dark matter ellipsoid, the central galaxy in the cluster is expected to just be a copy of that. All right. So what we expect is that if they're all ellipsoids, we see something that's round, we think it's an ellipsoid that's projected along the line of sight. And we measured this in the linear giants data, where clusters with the roundest shapes actually have weak lensing masses that are roughly 20% higher than the mean of the sample. those clusters with the most elliptical BCGs have weak lensing masses that are roughly 20% lower. All right, so actually the central galaxy, if you're able to pick it out and measure its shape, is a pretty good indicator of the way that the cluster is oriented. And so that was on laying the giants. And I have a grad student and Tayin an undergrad who are now trying to do something similar with the SPT and the DS data. There we don't have the nice X-ray low scatter mass proxy, so this is somewhat more tricky. But we do actually see if we use the SC mass as our mass measurement, what we can see is that clusters that are the same in SC mass and redshift, they actually have very different richnesses, in the sense that clusters with a round central galaxy have a higher richness, which is what we would expect, right? It means we have a cluster aligned along the line of sight, and we measure a larger number of galaxies. And all right, there's a few other things that might play into this. None of them currently fully account for what's going on. All right, but can I have a few minutes to talk about LSST? Two. All right. The other part of my current work is working towards the Rubin Observatory, and it's a legacy survey of space and time, which you might have heard almost in your shortration, but it's getting real. There's actually a picture from 2 years ago now. It's being a little bit delayed, but the main survey should actually start early 2025. And what it's going to do is it's going to map the entire southern sky for 10 years. There's an all-sky projection where this is the field of, well, this is the sky that LSST can see at a given time. So this is above 20-degree horizon. This is the zenith. And LSST will just point back and forth for everything in here. It has the capability to cover the entire night sky within 3 nights, which is going to do that for 10 years. There's a lot of motivations, science motivations that go over it. Obviously, the transient sky is going to see everything that changes within those 10 years. But dark energy and dark matter are both very strong science drivers. So the survey design will consist of many brief visits. I'm just going to revisit each field many hundred times over 10 years. Which for transient scientists, we get a great movie. For what I do, it means that we get weak lensing quality imaging over the entire southern sky. For every cluster in the southern hemisphere, I'm going to get ring giants like data. And so we can now do the ring giants analysis for much larger samples of clusters. Okay. And so the community has been preparing for how to do cosmology with LSST. All of this is organized in the LSST Dark Energy Science Collaboration, which has roughly 1,000 members. And so that's preparing to do cosmology with supernovae, with cosmic shear, there's weak lensing, galaxy clustering, highly delay strong lensing, but also galaxy clusters. And we've set up simulations of what the sky will actually look like. So people can go and start practicing on data, well, on images that look hopefully quite like the LSST images that we get later. But what excites me actually most is that there will be not only LSST, but there will be plenty of other surveys. We also have Rosita, which, yes, it got shut off because of the war, but it actually took 3 years of data. So we have 3 years of an old sky survey, a new deeper X-ray survey, with the first data being released this summer. So we'll have X-ray selected clusters. We also have a lot more of the CMB experiments gearing up, which will also find clusters in the SC. And so we're going to have our X-ray data and LSC data. In the optical near infrared, we're going to have LSST, and we'll have Euclid and Roman in space-based. And so in general, there's plenty of synergy, but especially for cluster cosmology, having these multi-wavelengths properties of clusters, with which we can use to build, in my opinion, more complex models of the relation between the mass and the observables, is a really, I think, exciting opportunity. I'm working on some of the more technical aspects too. In particular, both Euclid and Roman, they actually require LSST imaging or to photometric redshifts, of course. But this needs quite a lot of work in improving how we deblend fluxes from the various sources, as well as shape measurements. And so my summary is that clusters are, in principle, a very powerful pro of cosmology, but they come with a fair bit of challenges, as we've seen from the DSE1 cluster cosmology. But looking forward, I think there's a lot of synergy prospects between these multi-wavelength servers. All right, I'll stop here. Thank you.
Any questions for 5-10 minutes?
So I'm not really a weak lensing person, but when you're talking about the halos being here or and towards the edge, really they're kind of like a clumpy hierarchical system. Does that play a role, or does it average out? The fact that there's little clumps all over the place that would probably have stronger effects than anything like near them.
Yeah. So from going to the spherical cow, the full cluster, there's a few orders of complications. So you're absolutely right, they have substructure. The biggest one is the triaxiality. The substructure comes in addition to that. Now, we cannot fit for the substructure in weak lensing. But what it does is, if a cluster has significant substructure, it will bias the weak lensing mass that we get from just fitting an NFW model, right? So it'll bias it. Actually, it'll probably bias it low in most cases. When I say weak lensing masses are unbiased on average, what that means, if I pick a set of halos within a certain mass range, and I simulate a weak lensing measurement with all of the complications, with substructure and triaxiality and filaments, what I find is that the average mass is actually very close to unbiased. Okay, but things like triaxiality and substructure, they will scatter each cluster up and down. So this is actually part of why there's this intrinsic scatter of 20%. Even when we have Roman shape measurements and excellent photos, if we just fit spherical NFW models to our weak lensing observations, there will be an intrinsic scatter of 20%. I hope that answered your question.
Yeah.
I was wondering, for the cluster finding, have you considered using a overdensity based cluster finder as opposed to red sequence?
Yeah, so there's various groups trying to work on cluster finding. For, I'd say, low redshift data, and let's say that's redshift 0.5 or below, the red sequence method has a smaller scatter with halo mass than things that try to use all the galaxies. So really, if you're saying overdensity, it means that we also have to look at the blue galaxies and a little bit of the green galaxies, right? In the low redshift universe, those mainly just add scattering. Okay. Because the red sequence, that's something that's very specific to evolved clusters, right? That's only present if you have a halo which has been sitting there for a while, right? As we go to higher redshifts, this might become more important, where more of the cluster members are not on the red sequence yet. And there are people working on other cluster finders, and in fact, Euclid is not going primarily with RedMapper, but Euclid is also targeting higher redshift objects. They are tricky to get right, because if you do this on simulations, you require that the simulations are good at predicting the colors of galaxies and clusters, and actually terrible at it, right? Every single simulation out there that tries to do that has the wrong colors for cluster galaxies, right? They all have issues. And so it's actually very tricky to do this on the simulations and get it right. So when you do that, you actually have to go back and compare it to things like the X-ray and the Z observables, which you can only do for the more massive clusters, because we don't have the depth yet to go to the higher redshift and lower richness clusters. So yes, but I would say right now it's not as involved as the red sequence-based cluster finds.